Hi, my name is Jim, and today's topic is capacitors, and capacitors have capacitance. Now, this is an electrical component, and what we want to do is find out what it's good for and why we might need it. The symbol for this is two plates with wires coming into each end, or two plates with wires coming each end with a plus sign. And this is an electrolytic capacitor, and what that means is that it's polarized. It doesn't work well with AC. As a matter of fact, it doesn't work at all with AC. And this side has to be connected to the positive side of a power supply, else it'll break down very quickly. Now, the drawback of that is that you can achieve larger values of capacitance in a given volume if you use the electrolytic manufacturing process. So let's take a look at this. What a capacitor is built from basically is two plates here, and I've tried to show these in 3 dimensions. And think of them as aluminum foil with a wire connected to the bottom and the top, and what we have in between is called a dielectric. And for this case we have air. Now, I tried to take a capacitor out of a 1950s radio I'm repairing and kind of show you what it looked like, but I wasn't too successful in unwrapping it. But there would be 2 sheets of aluminum with wax paper in between, which are rolled up and connected to wires. And if the wires leave the ends of the capacitor, it's called an axial arrangement. And if they leave on the same end of the capacitor, is called a radial arrangement. So that would be the footprint of the capacitor, and you'd be interested in that if you were laying out a printed circuit board. So what goes on here is if we, say, have a voltage source and a resistance and a switch, and I have to have the resistance in there or I end up with some mathematical difficulties, and I flip the switch, what we would have is electron current, not conventional current, and I've shown that as E negative, flow into one plate of the capacitor that's connected to the negative side of the battery. And since like charges repel, electrons on the other side would be pushed back into the circuit, so this capacitor would assume a charge and eventually would come to be the value almost, very close to, of the voltage source V, and for the heck of it we could make that, say, 10 volts. Now, to think of this in a little bit simpler terms, suppose you have a hose and the nozzle's turned off, and you connect it to the spigot on the side of your house, and you turn the water on. Is what you'll hear is water running into the hose, and then the sound will diminish and finally stop. Now, what has happened is that the water pressure in your house has charged the hose just like the electrons here have charged the capacitor. So if your water pressure in your house is, say, 30 psi, which is kind of the low end of a well system where the pump turns on, that charging would be that the air inside the hose is being compressed by the higher water pressure, and when equilibrium is attained, then the water would stop flowing. Hence, when you would open the spigot, you'd hear the air spitting out, and then eventually some water would come out. So that would be kind of the hydraulic equivalent of charging a capacitor, would be connecting a hose and turning on the spigot. So we need measurements here. So let's just say that V here for the time being is 1 volt, and let's say that 6.242 times 10 to the 18 electrons are stored as charge on the capacitor. What we would say is that the value of the capacitor is 1 farad. So remember that this amount of electrons is referred to as 1 coulomb. So if we had that, what we would say is that the capacitor value would be Q in coulombs over V in volts, and that would be equal to the farad. So you can kind of relate this abstract label here of a farad into coulombs per volt. Now, a farad is a relatively large capacitor, and it's only been in recent times, the last 10 years or so, where farad and larger capacitors have been made, and they're referred to as either supercapacitors or ultracapacitors. Usually in electronics we deal with much smaller units, like the microfarad which would be 1/1,000,000th of a farad. That would be times 10 to the -6, or a nanofarad times 10 to the -9th, or a picofarad times 10 to the -12th. So if we take a look at this from the standpoint of the electric field, and think of this kind of like as a magnetic field, and we have a capacitor with charge across it, plus and minus, is what we see as electric field lines extend from the positive terminal of the capacitor to the negative terminal, and this represents a force. So that force would be proportional to the amount of charge, and would actually be trying to attract the two plates together if the charges are different, or repel them apart if the charges are the same. So this is referred to as the E field. And what I've shown here is called fringing on the outside, and that's kind of a bad thing in that it doesn't utilize the area of the capacitor quite as effectively as it could. So in radio waves we have two components to it: an H field, a magnetic field, and an E field, an electrostatic field, that propagate through space at right angles to each other at approximately the speed of light if it's in air. And if it's in fiber optics, that would be, say, light would be 66% of the speed of air. And if it's in a coaxial cable, saying electrical signal for cable TV, that would be approximately 66% of the speed of light also. So E fields are important not only in understanding capacitor, but in other related topics which are a little bit more involved. So this is what we need to remember: is like charges attract and unlike charges repel, just like with magnets. So if we're going to look at some the physical components of a capacitor, is what we would say is that the capacitor, again in farads, would be equal to the permittivity, and this is a constant that's determined by the dielectric. And the dielectric is what sits in between the plates, times the area divided by the distance between the plates. Now the area would be, as I've drawn that little three-dimensional guy on the other page, the square inch area or square centimeter area of each plate. So the dielectric sits in between here, and what that simply means is it does not conduct direct current. That's an important concept. Capacitors can charge where current will flow, but if we're feeding it from a DC source like a battery or a cell, once that capacitor charges, the current basically, except for a leakage component, which I'll talk about in a minute, goes to zero. This has very important implications in electronics because they can couple AC signals while blocking DC signals. For example, if you put a DC component on an earbud, like would be the headphone driver inside a player of some type, is what you'd hear would be a click, and then the AC would ride upon that, the driver would overheat, nothing good would happen. If it's connected with a capacitor, you'll still get the click for the capacitor charging. DC will not flow through the earbud, but AC will. So that would be called a coupling capacitor. Now we have our permittivity relative, and there's some other math in here, but I'm not going to get into it. And that's approximately equal for air of 1.0, and that's going to be our reference. And what's going to happen, as we see, is we can insert dielectrics here, which are non-conductive, that for a given area and distance between the plates will increase the capacitance of the capacitor. So for example here, let's just take glass, which has an E relative of 7.5, which means basically that if we use it, keeping this constant, is the capacitor is going to increase in value by a factor of 7.5. So think in your mind's eye that we have a 1 microfarad capacitor and we have an air dielectric, and what we're going to do is take a piece of glass and slip it in between those plates. What we end up with is a capacitor value of 7.5 microfarads. So that would be our first case of adjusting the permittivity of the dielectric. Case number 2 is, suppose we have a capacitor with a value of 1 nanofarad, And we're going to take the area of the plates, again, square plates we'll say, and double it. When we do that, we would effectively have 2 nanofarads. Case number 3, dealing with the distance between the plates. Suppose we have a capacitor of 100 nanofarads and we double the distance between the plates. Since this is in the denominator, our capacitor value would decrease to 50 nanofarad. So as a general summary here, and this is in a lot of textbooks, is that E relative for air is given as 1, and that's the reference point. Glass, as I mentioned, was 7.5, and we can get up to ceramics to go up to 7,500. So if I stuck a piece of ceramic in here, I'd be talking about a 7,500 microfarad capacitor. Now, why that's important is that we can make small, physically small capacitors with relatively high values by using ceramic as a dielectric. So in case 1 here, what exactly happens if we insert a dielectric other than air? So we'll just pretend here that this is glass, and what we'll see is that the red dots here is referring to the nucleus of the glass, which is basically silicon, and the black lines around it are the outer electron orbitals. And if we have a charge across the capacitor, what happens is that these orbitals will be stretched. So what it will appear to be is that the plates are closer together. They're not, but it appears to be that way. Hence, the capacitor goes up because the distance between the plates goes down. So the orbital are stretched, but they're not broken. If you break one of these, an electron will leave the orbital and enter the plate, and most likely another one down here will break and fill in the hole. And as we'll learn in a minute, that'll be called breakdown. And when you rip electrons out of orbit like this and you have breakdown, typically what you have is voltage and significant current equals power equals heat equals bad. The part has failed. Usually it's catastrophic. So if we take a look at the breakdown for several dielectrics, I only selected a couple here. For air, it would be 75 volts per mil, which is per 1,000 inch separation between 2 plates. For oil, that would increase to 400 volts per mil. For glass, 3,000 volts per mil. And finally, for mica, we end up with 5,000 volts per mil. And most tables usually do not go above mica. So as you can see here, the breakdown can very much be affected by the type of dielectric, and the capacitance value is very much affected by the type of dielectric also. But in no case is the part to break down. So let's look at a real capacitor here. Nothing's ever simple, right? So here we've got our main capacitor C, and in the leads and in the manufacture of it, we have something called ESR, that stands for effective series resistance. Also, we have another parasitic. This is not desired. Since there is wire, this is called effective series inductance. Now, we haven't talked about inductance yet, but it'll have a characteristic which is exactly opposite to capacitance. And what this does is it means that the capacitor is made less effective at high frequencies. We're not there yet. Also in the capacitor we have a large R in parallel with it, which is called the leakage component. So it's going to discharge. For example, if I charge the capacitor up to some value here and took it out of the circuit, which I'm going to do in a minute, it would hold charge, but gradually it would discharge through the leakage resistance. So this is due to imperfections in the dielectric. Further, we've got this little guy off to the side here. It's a C in series with an R. It's called dielectric absorption, and this is kind of a nasty attribute. If you discharge a capacitor, where you'd think that there'd be a balanced number of electrons on each plate, walk away, come back 10 minutes later, you'll find a voltage there. And when you're dealing with, say, older devices like picture tubes, where you're talking about 25,000 volts, which have notably high dielectric absorption, you can get lit up even though you've discharged the capacitor for a minute or two. So this causes some problems. We won't speak to them now. So in summary, I guess we could say that a capacitor stores charge, which is Q in coulombs, and it also stores energy, which is rated in joules. And the equation for that is W equals 1/2 CV squared. So what you can see here is the amount of energy stored in a capacitor increases as the square of the voltage. And you have to kind of be careful of this. For example, in a microwave oven, typically have a 1 microfarad capacitor operating at about 1,000-1,200 volts. There's a lot more energy stored in that than, say, the little 10 microfarad guy 10 volt guy I'm about to use here in a second. And this can actually kill you. So you always have to be careful when you're dealing with capacitors, not only from the standpoint of the current they can deliver when they're shorted, but also from the standpoint of the voltage and energy which they can deliver. And you don't want that through your body. So what I've done here is I've charged up a little capacitor here. This has a value of 470 microfarad with a breakdown rating of 25 volts. And I'm going to disconnect it from the circuit here. So this should be charged. And next I'm going to take a light emitting diode. And if I get the polarity right here, we can see this discharge. So at the present time, the energy or the voltage in this should be maybe about 1.5 volts, because this lead has a general forward voltage drop of 2.2 volts, so didn't take it all the way down. And if I do it again, you'll see that nothing happens. So I can actually walk around with a charged capacitor. Is it discharging? Yes. Not enough to stop me from lighting a light emitting diode after I took it out of the circuit. Now what we're going to do next is just take a little look at this breakdown phenomenon again with a video clip. And when you're looking at this, what I want you to think about is safety glasses. It's recorded originally, it's from YouTube, and then I've, using some software editing stuff, did a slow motion on it forward and a slow motion on it backward. And then after that we'll come down and talk about the charge and discharge voltages and so forth.